Pleasure to introduce Ilya Vinogradov from Bristol, and he will be talking about effective Ratner Theorem for ASL and distribution gap between sequences.
Okay, well, thank you for the invitation and the introduction. And I guess you can hear me, right? Since I can hear myself much better now. Okay, cool. So before I forget, pretty much everything I will talk about will be joint work with Tim Browning, Bristol, unless there is more time, in which case some results will not be joint with Tim Browning. Right, so I'm going to talk about randomness in certain sequences from a certain point of view. So, so I'm going to take sequences in 0, 1, the interval 0, 1. So let's take C1 through Cn, and it's a bit wobbly, in 0, 1. So we can assume, let's say, that the sequence is uniformly distributed as n goes to infinity for starters. I won't even write that, and everyone knows what that means. And I'm going to consider what is called the gap distribution. So first thing to do, I'm going to find that for a general sequence. So to do that, we first reorder the set. I usually just, do this. So I say, whatever repeats there are, you put them in a primed set like this, and here the condition is that the primed guys go in increasing order, not decreasing order. Okay. So now we can understand what the gap distribution means. So this board doesn't go up. Okay, so definition will be here. So definition. So again, we have this parameter n. We have a positive number x, and we define lambda sub n of x to be the fraction of gaps whose length is less than x over n. So that means we take j from 1 to capital N, and we take the gaps. So the obvious convention when j is the correct, like j is n, exercise. Okay, so for nice sets, for nice sequences, there will be capital N gaps. Well, there could be a little fewer if you have repeats, and then you have 0, and then let's count it, and so this ratio makes sense, and it's typically order of 1. So what can we say about this? So let's look at at the random case first. So when Cn is a realization of a random process. So specifically when they are IIDs, then we take almost any realization. Okay. So suppose the sequence, Cn n equals 1 to infinity is IID, and we take, this is, well, not just So it's a generic realization of this process. So almost any realization.
IID uniform, right?
Yes, so, a little bit, absolutely, yes. I just spelling accordingly for local preferences. What's the realization of uniformly identically distributed, what's better? Random variables. Okay. Then what we have is this, that lambda n of x converges as n goes to infinity to a certain function lambda infinity of x, which happens to be the exponential distribution. This is an exercise, right? This is for every x. If you want to do the integral, it's also an exercise. There will be a similar integral that will be much harder to do with a different function here later. Right, so the density is this, minus t. So in particular, it, obviously it has exponential decay probability of having small gaps, large gaps as small, exponentially small. So in the early 90s, I don't remember exactly when, Boshevnitsan began studying certain fixed sequences, so not random realizations, from this point of view. So what is the limit of the gap distribution? So this down. So I will go before 95. I'm not sure when. This was done on a computer, so this was probably simpler programs, but they were already sort of available. This is numerics, yeah, numerics. Numerics. Yeah. So he observed that if you take sequences of this form, n to the alpha, log to the beta n mod 1, for certain alpha and beta that I'll mention in a second, that, well, you always get a limiting distribution. Yeah, by the way, there should be some way to say which sequence this comes from, but I dropped that. Yeah, I'll just, whichever one is clear from context. So for such a sequence, Cn, so lambda infinity always exists. Right, so so you pick alpha and beta, so the sequence is uniformly distributed. So don't pick alpha equals 0, beta equals 0, don't pick alpha equals 1, beta equals 0, and so on. Pick only the ones that, that uniformly distributed. So lambda infinity seemed to exist, and there were two cases. So I'm going to refine this a little bit. So there was a special case, which was alpha equals to 1/2, beta equals 0, and there was the other case is, well, everything else. And in this case, this was some a non-universal distribution. And then in everything else case, it was the exponential distribution. Okay, so this was what the picture looked like on the computer. So, right. So, as you know, usually the random case, which is this, is harder to understand than the non-random case. So I'm going to specialize to this case now, only to the case of square root n mod 1. Yeah, if I put alpha and beta in the right place, it should be square root n mod 1. Okay, there should be color chalk here. Where is it? Yes, okay. So we specialize to this.
Nowadays, know that this is the only strange case. I mean, this is numerics, right? So
this is numerics.
It could be that there are others that people haven't studied.
It could be, but the numerics look pretty convincing, and so this.
Oh, but you can plot any value of alpha and beta.
Yeah, you can plot. Yeah, whatever you plot, you get this, except this case, if you plot.
And is it proved for any values of alpha and beta?
That's what I'm going to get to next thing. My talk. Yes. Another question?
No. Excellent. Yeah, I want to hit.
Oh, good. Okay. Okay. Let's see. So I guess the down is easy. No, I should leave space, right? Right. So the only known case is the non-random case when alpha is 1/2 and beta is 0, when the distribution is non-universal. So this is a theorem of Elkis and McMullen. This is from 2004, and they show that, yeah, so everything now specializes to this yellow sequence, everything I say, that lambda infinity exists, and it looks like this. So this was the reason for not evaluating that integral. So there is some continuous, slightly more than continuous piecewise analytic density. So yeah, if I were to write out the density, it would be much worse than all those equations that you saw in the previous talk. It would take up a few boards. But the essential points are these. So I'm going to plot f of t. So between 0 and 1/2, it's nice and level at 6 over pi squared. And between 1/2 and 2, it's given by another analytic function. And after 2, it's yet a third analytic function. So there are some derivatives here that don't match up and some derivatives here that don't match up. And so I should label this, right? Let me label this. So this is going to be f of t. And we can also plot the exponential curve. So 6 over pi squared is less than 1. Exponential, that guy starts higher up. And, well, at some point, it goes down really fast. It should be far below, well, this is not very good. It should be far below this power tail here. So this should be the exponential curve. And another fact of this, for example, is that f of t is asymptotic to 3 over pi squared over t cubed as t goes to infinity. So it has a power tail, unlike the exponential distribution, so that large gaps are reasonably likely.
In particular, this limiting distribution has finite first but not finite second.
That's right, yes, and has finitely many moments given by exactly the asymptotics you see. Okay. And yeah, so they have an explicit formula, which I said will take a few boards. But this was, yeah. And it's realized nicely on ASL2 or mod ASL2Z, which is where I'm coming to. Okay, now, any questions while I check what I skipped? Oh, right. So here's how I view this problem, and why I like it better. So we start with a number theory problem. Trevor? Yeah? Okay. Start with a number theory problem. And it is solved using dynamical systems. So specifically, Ratner's theorem. So since this problem is solved using Ratner's theorem, there is usually no rate of equidistribution, which is what I'm going to get to in a second. So what I'm going to do today, basically have the error go the other way. We'll replace Ratner's theorem by some number theoretic results that feed into the dynamical systems part, and then return to number theory, get a rate for square root on mod 1.
So you're going to get a rate in lambda n in that limit up.
Yeah, I'm going to write the next theorem, right? It looks like you know. Okay, no.
I told you I would heckle you yesterday.
It's not heckling, it's like my talk is zero entropy, you know exactly what's going to happen next. Or you have some filtration there that knows my next step. So, right, so here's a theorem of Tim, Brownian, and myself. So, right, so what could not be obtained here was a rate for the difference between lambda infinity of x and lambda n of x, because it relied on Ratner's theorem. Which I'll show where it came from. And what we show is that lambda n of x minus lambda infinity of x is less than, I guess, some function of x. Don't ask me about the function. And this for some positive delta. Don't worry too much about the delta. We cannot get an optimal delta using this method. So as n goes to infinity, the difference shrinks at a certain power rate. Okay, so well, we have one fixed sequence, and you take it to infinity. So delta depends on on nothing. But what does it depend on? In another sense, I guess there will be an equidistribution theorem, which will have, like all of them, a certain norm. Well, and that norm is not particularly well optimized, and it will, you pay a very heavy price for having a function that's not smooth. Right? So, but no, it's just. I guess there should be some power, but that's best possible. We have no idea what it is, And the power should not depend on anything.
And uniformity in C.
So it should be bad when x is large. It should be bad when x is small. And if you want, things don't behave well when x is a function of n, and that goes to 0 too fast or goes to infinity too fast. Basically, because, for example, you can trivially see where the shortest gap is, and there is some gap. There is a limit there, and this function capital F, we also understand, we know sort of what's the integral from 0 to something little, and we know what's the integral for the tail. So there are some natural constraints. So it's just silly to take x really,
To see some wildly blown up function in infinity and 0.
yeah, there are issues at both sides. Okay, so right. So now I'm going to show how this connects to the original problem connects to dynamical systems, homogeneous dynamics. This will be straight from Elkis and McMullen. No, the secret is I will not be able to get this board down. Maybe I'll need that. Oh, no.
You have special equipment.
Special? Where?
Special stuff.
Ah,
The bamboo stick. Yeah.
bamboo, right. Okay. Make sure nobody falls asleep.
You also have the other one for. You want to make sure no one falls asleep.
Okay. You're in danger. Okay. So right. So instead of dealing with this function, right. So this is going to be from gaps to, let's say, G mod gamma. Right. So we're going to analyze not function lambda n, but a slightly different function. So we're going to define sigma n of x, which will be the total sum of all gaps whose length is less than x over n. So this was the fraction of gaps whose length is less than x over n. This will be the total, the combined length of those gaps. So one way to write it is this. So lambda n there is a non-decreasing function, so we can write this integral, or I'll also say just total length of gaps less than x over n. So of course at infinity it's 1, at 0 it's 0. And same by the way for lambda n, and this is also non-decreasing. Okay, so what goes next? So, right. So, I'll tell you what I skip over. So first, we take n to be a perfect square. This is sufficient. This is one lemma in one 5-line lemma. That is, if there is a limit for the square sequence, and then there's a limit for the full sequence, and they're the same, basically. Then we need to do an approximation of this square root n sequence. So we're going to move the points a little bit, so the limit doesn't change, but so that it looks better for us. Okay, so these functions don't change very much. Put in these, you frowned. No? Okay. So here is how we do it. I better get this in the correct order. Right. So how can we write square root n mod 1? Well, I can write it as square root a plus b minus a, where, well, this is done in an intelligent way, so to speak. So I mean that a squared plus b is n, a is as large as possible, b is positive. So, for example, b is between 0 and 2a. Okay, so I just want to write it like this. Basically, this is square root n, this is the integer part of square root n. That's what I want to do. Right. So this defines a and b, and by this convention here, right, a is between 0 and is it s plus 1 or s? Maybe it's s plus 1. Okay, this is s. Now, so suppose you're a point on the circle. So how do you know which gap you land in? You need to find your neighbor on the right and your neighbor on the left. That tells you the length of the gap, and then we're going to sum the lengths of short gaps, and that will give us sigma. So here is how we're going to find the length of the gap where you are. So let's call it L. So n is how many points you have, and t in 0, 1 is where you are in the circle. So this is the point that you are. T is in 0, 1. So it's going, we'll multiply by n immediately to normalize it. Right, yes. Then we're going to look for the neighbor on the right. How does that look like? Well, we're going to take a certain function r of t, of ab, and look when it's positive, non-negative, I should say, and subtract the left neighbor. A and b in this range. So what are these functions? R of t, ab, is square root of a squared plus b minus a. This is square root n. Take away t. So this function does exactly that. This is distance to right neighbor, distance to left neighbor, when you with a negative sign. When you subtract them, you get distance between right and left neighbor. You scale it up, you get the length of your gap. Okay. And so the trick is to replace the function r of t by another function. This is okay, so we're going to approximate it by a natural function. So so here's how we get it. So we start with this function, right? And we what do? You just have to rationalize the numerator, right? Otherwise it doesn't look right. So let's do that. Okay, and now we're going to do an approximation which requires a few lemmas. So you see this a squared plus b here, appears here, appears here. If we have a neighboring point that minimizes something or maximizes something really close to 0, well, this is small. And this requires a justification, but basically I'm going to take this and put another a plus t instead of that. That's going to be the approximating function. Okay, so all I'm saying is that for most t's, for a close to full measure set of t's, these functions, this let me write it again, and the original r of t will yield the same quantities. Okay, so the advantage of this function is that it doesn't have square roots. It has polynomials, and Trevor likes, well, some people like polynomials. Many people like polynomials. This function is even better because, well, what do we have in the numerator? We have b minus 2at minus t squared. So a and b are the integers here, and t is something in 0, 1. So it looks like an inhomogeneous linear form mod 1, right? Because b will be chosen to make it mod 1, the numerator.
Sorry, I'm just a little confused.
Yes.
There's an e in the denominator.
Yes.
So it's not really a polynomial in A.
No, it's not a polynomial in A, yes, but you'll see. 1 second, okay? So what does this have to do with homogeneous dynamics? We need to get a lattice in here, right? So I'm going. This is the function that I can sort of.
Can you explain again why? So you're saying that these two you can approximate one with the other?
Yes, and for most t's, I can approximate one with the other. I can control. For most t's, t's in 0, 1. For most t's, they're close. That's what I need. Effectively, this is all very explicit, right? You just do it. I mean, this is yeah. Or you see the paper of Elkis and McMullen, they do it very carefully. So what's the connection to lattices? Right, so I guess I really briefly define SL2R semi-direct R2 or ASL2R. So I'll do it here. Yeah. So so by this group, I mean we take SL2R semi-direct R2, which I can think of as a matrix 2 by 2, a vector or a column vector of zeros, a row vector v, and the number 1 in SL3R, multiplied the same way. like in SL3R, so I can write either matrix comma row vector, or I can write this full 3 by 3 matrix is the same thing. And this group acts on R2 naturally, so if I take X, right, MV is the same thing. If I take X in R2 and act on it by MV, this is XM plus V. This matrix multiplication, X is a row vector always. Okay. Or I can take, alternatively, I can put X1 and R3 here, just do matrix multiplication. Okay, so here is how to realize all of these quantities on homogeneous space. So we have the letter S there, so let's use S, right? S is going to infinity, so we're going to take this matrix. So what I don't write is 0. We're going to take a unipotent matrix here, 1 minus 2t, 1 t minus t squared. Okay, so this is my matrix, this is my vector. And here we're going to act, so if we want to act on R2, we can write it like this, A, B, 1. Okay, so you can check that, well, if S is going to infinity, then sort of this thing has two expanding directions, this one and this one. They expanded by different powers. This one is expanded more, and yeah, and it gives you what you want. So let's do this. So this gives us A plus T over S. Oh, actually, I know the last component. That's 1, right?
Well done.
Yeah, and guess what? This one is going to be 2. So it's S. Sorry, B minus 2AT plus T squared, which looks awfully reminiscent of what we want, right? So now all we need to do is to understand what is sort of the function of the homogeneous space that is going to capture all this minima and maxima for us, right? Yeah, so basically if you just think of dividing these like and by putting a 2 there, this gives you exactly the function rho. So I'm going to call this, oh no, I need another board first, right? Before I call anything, I need another board. So I'll get rid of this. So we're going to take W1, W2 to be our R2, the plane, and right. So what condition do we want there? We want W2. I cannot see it, but you can see, right? W1 over 2W. W2 over 2W1 is rho, right? I can't see, so I just have to do it from memory. This should be rho. So basically what we want is this. So if you think of what this plot is, we're going to have a triangle, looks like this, and we're going to take these guys, the sides. So, yes?
I seem to get an S square times rho there.
Yeah.
Say it again?
I seem to get an S square times rho.
Right, S squared is here, right, yeah. Okay, S squared is n, sorry.
Oh, okay.
Sorry. Right, so we want to, what did I want to say? This should be like 1, 2c plus, and 1, 2c minus. C minus is negative. The area of this triangle is c plus minus c minus. And judging just by what the minima and maxima tell us, we want to arrange for this triangle not to have any lattice points inside and be as large as possible with this property. Let me get it. So, well, basically, loosely speaking, it means there is a lattice point on this side, a lattice point on this side, and you cannot open it up anymore. Is this interpretation clear? So for any lattice, the function we're considering is this. We take, we're going to take C plus and C minus and make C plus as large as possible, C minus as small as possible, so that the triangle thus formed, well, this is 0, 0, contains no points from the lattice. So the convention when we have a point here is that, well, we just say the area of this triangle is 0, and if there are no lattice points here, you can keep expanding and just say it's infinity that has measure 0. Okay, so then for every lattice we can define this function, which would be 0, infinite. Almost everywhere finite. Okay, so this is the function, which is very not smooth, to which we are going to apply the theorem, which I'm going to talk about next. Okay, is this picture?
What is the connection with the area of this triangle? What is the relation with rho? Or with the
Right. So the area of this triangle will be this.
So the area of the triangle will be that. Oh. Can you explain it in one?
Okay. Right. So we're going to take r or rho of t as small as possible, which means that's the positive guy. That's the corresponds to C plus here. This line is not the color here. So that basically we take the nearest lattice point and use it to construct this triangle. And similarly here we use the next the closest from the lattice point closest from the other side to construct the triangle.
Sorry, so I'm just won't get confused. So you're really saying that ln of t is this function tied to some is to something active on the orbit, right?
I'm saying that what am I saying? So if you look at the set of t, where ln of t is less than x, take the length of this. This is just a bunch of intervals. Sorry, just a bunch of intervals. This is sigma n of x. Sigma n of x. This is the total length of intervals that have length less than x over capital N. That's what I'm saying.
No, yeah, but you still haven't shown us a dynamical system, right? Because
I have not. A dynamical system will come from this.
right, but you haven't done it yet.
I haven't not done it yet. Correct. Yes. I'm just. Well, I hope this would at least motivate the transition to dynamical systems, because there are a few more small lemmas that one needs to take care of. A few.
Wait, what lattice are you looking at here?
Right. So I'm about to state a theorem, which will for the theorem I need a function, and there will be a weak limit of measures, and it will be something. So I need the one particular function will be of interest. I'm describing that function to you, and which lattice I take. Well, there I'm going to take a lattice which is this. This is lattice Z2, and then you apply this unipotent element and then expand it by this diagonal element.
Oh, so, okay.
Right, and then the measure of t's where, yeah, okay.
So the set of all things on the right hand side where a and b come from integers.
Yes.
Okay.
Yes.
But you're just saying that ln of t is this function applied to that unipotent of the unipotent. The function is a function space of lattices. I don't know if you have.
Yes. Yeah, I haven't written it yet.
And so you're saying that ln of t is basically that function
Sigma n of x will be that function.
Sigma n of x is that okay?
Yes. Up to some little.
So it's-
There are some bad ones, like some ones and zeros you have to throw out first, and that's okay.
This is a shifted lattice, right?
Yes, it's a translate. Yes, I call it lattice still for brevity. Yes, affine lattice, translated lattice. Yes.
So, but this is defined for the ones with the origin.
This is defined for anything, but it's interesting for the affine lattice. Well, you can always ask, what
You drew it with the origin indeed. So
No. So these red lines have nothing to do with the lattice.
Okay.
I did not draw the lattice. The lattice could be this, right? So lattice is green. Where's green?
The only points in the lattice that you've drawn are the green.
Yes. The lattice could be this. And
Okay.
it doesn't know anything about the origin. Okay. Right. So I guess I want to get rid of one of these, and maybe I'll need the help of that thing. Okay, so what Elkis and McMullen proved about well, that dynamical system is the following. Then I'm going to soup it up and make it a little better. Same paper. So they showed that for f bounded continuous, x is, so g is, right. So G is my group, ASL to R. Gamma is the integer point.
Sorry again, so in this definition, you are looking for smallest triangle with no point inside the interior.
Largest triangle
Largest triangle
with no point inside the interior, correct. Yes. And G mod gamma is X. Okay, so this is a bounded continuous function. So we're going to say this. So let me write it the same way. So this is the unipotent. I'm switching notation to X now, I'm sorry. So this is the unipotent matrix, and this will be Y. I usually like calling this X and Y. I hope this doesn't upset anyone, and as a matter of fact, Y will be the reciprocal of like X or something. So this is meant to mimic X plus IY, but it doesn't even do that. It will mimic 2X plus IY or minus 2X plus IY. So I'm should I put it back? Make it consistent? Yes, sure. Let's make it consistent. If I get lost, it's not my fault. Okay, so here S is going to go to infinity. We're going to integrate in X from 0 to 1. And so what Elkis and McMullen showed is that, well, the limit of this as X goes to infinity is equal to integral over the whole space, and mu is the Haar measure on X. Probability measure. Okay, so this used Ratner's theorem. That's the key input. So here, and hence no rate. I'll give this a name. I have F. So the slightly improved version, well, the effective version of Tim and myself is this, that that would be a hypothesis. The same integral of F, I should call it, I guess, I sub S, take away integral of F over the whole space is at most some constant times, that's why I wanted to use Y in the first place, right? Yeah, okay. So there is a norm of F, let's say C8, so F needs to be in C8. And so scratch work on the side, S is 1 over square root Y. So if I want to write Y to the 1/4 log squared Y, I better write S to the, this is so difficult, S to the 1/2 minus log squared S. So, and this is for S, let's say, greater than 1. Yeah, so for S large enough as S goes to infinity, this should hold. If this is correct, then this is I'm not very good with the board. Okay. Right, so for Y larger is better, for S, well, more negative the faster the decay. Okay, so this is an effective version of the previous theorem. This is C8. So the suprema of the first 8 derivatives need to be bounded. We can do a little better, but the amount of payback you get for, it's small, maybe 7 minus 7 plus epsilon. Okay, so the interesting part is the power, where, well, now I'll talk a little bit about that. Yes? Yes. Yeah, and before I say something about the optimality of the power, I should mention why this is non-trivial. So it's basically because this flow on the group has there's a two-dimensional unstable manifold. So basically something here, and if these were independent, you were integrating over an absolutely continuous measure, or with respect, yeah. So then everything would be trivial by thickening. But this is a really small codimension 1 submanifold inside the unstable manifold, so it's not entirely obvious. And the group is also quite small. It's not semi-simple. It's just basically this group, isomorphic to R. So we cannot just say that it's, you know, its orbits equidistribute nicely. That's not, well, as far as I know, that's not too easy. Okay. Yeah, which is why Elkis and McMullen couldn't do it, right? 1/8, see? That took you so long? 1/8? No, this is correct. Everything else I don't.
No, I think it's 1/2 was right.
1/2.
Yeah. S to the -1 is square root of y, and then square root of y to the 1/2 is y to the 1/4.
Oh, this is profound.
Yes. I proved myself.
Okay, I guess I won't get a chance to reuse the upper boards. Right. So I should say how the rate compares to similar results and less similar results, right? So I guess by now standard result holds for SL2 R mod SL2Z, not ASL. So this is a bundle over SL2 R mod SL2Z with torus fiber. So I think this is Sarnak 81, right? So you prove that if you put a measure on closed torus cycles, this, oh right, I should write it out. So here, I mean, y is going to 0, and this is meant to mimic x plus iy when applied to I in hyperbolic space. So he showed that this is equal to, for f, let's say, C infinity, I don't know, compact support, nice in every way. This is for SL2R mod SL2Z. Compact support, sure. So what did he show? He showed this is the integral of, well, he showed more, but the integral of f d mu of y plus little o, as little as I can make it, of y to the, this should be 1/2. Okay? So, I think I got this right, yes? Right, so this is 1/2 and this is 1/4. So either this is slower or we haven't exploited the method fully or something like that. And indeed, in the proof, it's basically, it's there is hope for improving this with some perhaps more number theory than I know. But for the method, this 1/4, half of what is there is the reasonable thing to expect, actually. Yeah, so if we get something too good, then, you know, we are equivalent to the Riemann hypothesis, right? So a side remark, if we get 3/4 minus epsilon for every epsilon, then this is the Riemann hypothesis. So we're nowhere near that. Okay, right, so a natural question to ask now is, well, what happens if you put a density here, right?
Just to be very clear, you're taking y to 0.
No, yes, y is 0, yes. So it's a long, closed torus cycle. I thought, you know, the experts know this, what goes to 0, what goes to infinity. It should be obvious.
Which point you're applying it?
Oh, God.
Applying it, yeah. You're applying
Gamma, well, that gamma is the, okay, gamma prime. Yeah, I'm lazy. When it's the identity, I don't write it, you know what.
also for one specific copy.
Yeah, let's just say this. Yeah, he proved it for other group. Yeah, that's okay. Right, so a generalization which looks a bit different is what you get when you have a density here. So then, yeah. So what happens then? So now I integrate over all of R. I apply to the identity. take the same group. I'm just going to write the thing that I like. This makes, so this related to S in that way. Assume some nice things about rho, like, and about F, so F as before. For rho, assume non-negative of integral 1 as regular as will appear in a second. So as y goes to 0 again, this is going to be equal to integral of f d mu plus basically the same thing except for some unfortunate things. So we're going to take eta between 0 and 1. Well, it's not unfortunate, it's just the way it's useful for. I'll tell you what in a second. So we still have 1/4, have a log y, absolute value, to a certain power, which I'll tell you in a second, and some norms. Oh, this is always the same norm. If I forget to put a b, it means the same norm. So remove the first derivatives.
And this k depends on.
I will tell you what k is in 1 second, yeah. Well, you don't want to know, actually, but once you learn what it is, you don't want to know. Right, so something about rho. So I take the L1 norm of the first derivative, raises to the power, say, eta, and I take the L1 norm of the second derivative, raises to the power 1 minus eta. So first I'll tell you why this strange thing. This strange thing allows you to take rho that is an indicator of an interval, let's say, and only lose epsilon in the rate. And if you want to have more overhead with some other norms, then you can do it without the strange thing with eta, right? And okay, what's k? Right. So currently k is 167. Right. So some work might improve this easily to something more sane, like 2. Well, not 2, but something more sane. K? Sorry? K does not depend, no. So k, yes. So as I wrap up, I'll say why k appears and why this is a bit different from that. Because normally, in dynamical systems, usually it's the same thing. But here the tools involve a slightly different tool. So, well, very slightly different tool. So it's a little different. And right, so I should say that all of these results are inspired by recent work of Andreas Strombergsson, who's here, and whose result I should quote. Also, for so take the same setup. Oh, right. I realize now. No, it's fine. That's all fine. It's all fine. Yes. Okay, it's fine. So we're going to take following. So I'm going to look at long closed torocycles, but I will embed them in a strange way. So I'll put them in ASL 2R, mod ASL 2Z. How do I do this? Well, I take this the 2x2 identity matrix. This is a diaphantine or something vector, row vector. So now this is a bit slanted inside our space. If you will conjugate it, if you secretly put the inverse, you can take a function here, maybe put a density, and integrate over R. Assume saying good things about the density. So this is one of the many things that's proven in that paper. Right. So shown that. So just by using Ratner's theorem, you can show that this is for every irrational xi. You get the Haar measure in the limit, but the rate is the new part. So this is what I'm going to write down. So we have again y is going to 0 here, plus big O of so the power of y is interesting. So some constant that depends on xi. I think the best possible is 1/4, right? So best, this is like optimal 1/4 times norms of f and rho, which are pretty much similar actually. I think it's f times some norms. And there, I don't think there is a log here for decimals. Okay. Yeah, and if you do the same thing with the eta, there will be eta dependence here. Okay. So the tools are very similar. And now, since I have all 3 results on the board, and time is running short, I'll just tell you what sort of tool replaces Ratner's theorem in each case. Yeah.
For SL, not ASL.
Really? What? So if you don't have this, then this will be for SL. If I have this, it's a slanted inside space. Yeah, so that does the full. Right, so I need a different colored chalk that is visible, like yellow. Oh, there's yellow. Okay. So what do we need here? Well, no, I guess I start with that. That might be more familiar to people. Right, so the proof starts with a lot of Fourier expansion, and then basically one just has to obtain after some work, a decent amount of work, one has to obtain cancellation exponential sums. In this case, a lot more work follows. And the exponential sums are as follows. So in this case, you want to get any savings whatsoever. This means e to the 2 pi I something. Trevor, not for you. In this case, it's this sum. It's actually a little more. I won't. There. So we're going to sum d from, let's say, 1 to c and d relatively prime. And so this means any integer with this property, just the inverse, multiplicative inverse, which exists in c and d relatively prime. These are called Kloosterman sums. Let's call this k, let's say, of m and c. Oh, I did it the non-conventional way. Yeah. Okay. So cancellations for this, any cancellation for this, systematic for every c, will give some savings in the end. And so the best possible, somehow, on average, well, of course, you don't expect it once, say, m and n are multiples of c, but on average, typically you get square root cancellations. So for this sum, you want square root cancellation. That's what gives savings here, which is known. Okay, and what else should I say? Okay, now I'll tell you what the thing is here. Here, well, you see we have a square, right? So this x is squared, so there better be a square there. Right, so here we're going to take almost the same sum. Right, so it's going to be pretty much the same, except there will be a square here. So c and d relatively prime, and c is between 1 and d. And again, square root cancellations for this, on average, will give these savings. Now, yeah, I should say now what happens to this one and why this is ugly, or less pleasant. Here, the sum is a little more involved because basically we have to do another Fourier expansion. Once you do another Fourier expansion, you have another term. So there's a linear term as well. Did I get this right? This is the wrong way, yes. D less than c. And c and d relatively prime. Right, so we want square root cancellations here, which also take place. But there are some more issues to take care of in this sum. So the 167 came from 168, right? And that comes from some things going not so well for primes 2 and 3. That's basically a lot of those put together, and some 7s there as well. Well, not the prime 7, just the number 7. The only primes where the issues are 2 and 3. Okay, right, so these are the only tools used. Now, as you can see, there are 2 variables. There's c and d. And as it happens, when we dig in, we only seek to get cancellations over d in every case. That's what I advertised. And there are two variables, c and d. So if you magically manage to get cancellations over both variables, this 1/4 will go up, has a chance of going up. C and D come from a certain Fourier expansion. So no, everything happens on tori. That's the stuff I do really well now. Yeah, it's on like T2 and then T1. That's kind of easy stuff. Yeah, yeah. So it's from that point of view, it's very simple. But yeah, right. So to improve this, we would need to have a certain sum of guys like this or like this or like that with a very strange weight in front that is not usually treated by normal number theorists. So that doesn't look very promising, at least to me, at this time. Now let me see what I forgot to say. I'm sure I forgot half of my talk. Yeah, there was another thing I wanted to say if I have time, but I guess time is running out. So I'll just say very briefly that what we can, well, another natural question is what happens not to bounded functions but to unbounded functions. So this is not joint with Tim Brownian anymore, but we can take certain unbounded functions of permissible growth and exclude a certain neighborhood of 0, and then we also get convergence for those functions. Say it again? This is where you're sort of flat. You have to enter the 0. And what this means for the sequence square root n mod 1, since everything is related to that, it means that, for example, if you take square root n mod 1, remove the perfect squares which pile up at 0, then the pair correlation function converges to that of the Poisson process, as a matter of fact. And yeah, basically, yeah, we also get convergence of moments up to order 3 minus epsilon. So that's as good as it gets because limiting distribution doesn't have a third moment. Yeah, so this problem is sort of analyzed from 2 points of view. So it's both the rate, which I explained in more detail, and some allowance for unbounded functions of prescribed growth. Okay, so I guess I just thank you.
Does your method stretch to getting things over shrinking intervals in Y?
So you,
I mean X, I guess in this case.
in X, so you just go to this theorem and you put in your density, right? And then what
with any density you want. Okay.
Yeah, this is if you will, this is an inequality. This take away that in absolute values, less than a constant.
So here in this cancellation of the exponential sums, you're using van der Kolk.
No. This is
Yes.
Bay conjecture
So-
from Beatty.
No, weight conjecture is for
So
not for the polynomials.
right. So the actual paper that we use is by Cochrane because we need it not just for primes but for prime powers. But basically, it comes from the Riemann hypothesis for finite fields.
Yeah, but that is the original Klosterman sum.
Yeah,
not
yeah.
the polynomial one.
Right, exactly. That's why these are somehow more natural to deal with. That's right. And these are a bit strange. So everyone knows something about that, but not everyone knows something about this kind of stuff.
So this is also, in this kind of picture is also known for polynomials in terms of t or only degree 2?
So this will be known for any curve. You just look at critical points for every prime, and then your rate depends on what the multiplicity of the critical point is here. But from the point of view of equidistribution, this will no longer be helpful.
So what I'm asking is,
Sorry.
can you do the semi-direct product with an irreducible representation of SL2 rather than just the natural representation?
I see. So I haven't thought about higher dimensional representations. I think it would be similar. But just 1 second. No, basically, I don't know off the top of my head whether I can do that. But I can tell you, if you decide to put a cube here, then I don't know how to do it at this time. Yes.
So I mean, but these exponential sum estimates you can handle for any polynomial.
That's right. The exponential sums will work regardless. It's just if you change these functions, for example, you will not get a sum of the form that you like.
Mod p or mod powers of p?
Sorry, what?
Mod p or mod powers, and there's exponential sums that
You can do mod powers. Right. So
I mean, a kind of result like Langway, just a half or half of the dimension.
Oh, you mean if you have a multivariable?
Yeah.
Multivariable.
Yeah, so I mean, there's all this work of Adelson's so you expect square root cancellation, and that's with some degenerates. A point of defined by the Question.
Yes.
So this is all about square root of n.
Yes.
So is anything known about?
So nothing is known.
And what is the abstraction to dealing with?
So what's the problem, right? So something used to be on this board, which I can see, but you cannot see, I suppose. So when we take this function r and replaced it by rho, a magical thing happened. We got an inhomogeneous linear form. That ceases to be true if you take n to the 1/3. So for n to the 1/3, this rho function, which was here, so now some of you still have it, is going to be a cubed plus b minus a plus t cubed 3 plus a plus t squared. This is just the derivative of that. This is going to be rho. Now what you see in the numerator is no longer a linear thing. So I don't know how to understand the point closest to the origin. How to analyze. I mean, I understand, I just don't know how to analyze it. So for anything you can get to this kind of rho t, let's say without roots at least. That you can do. But what happens after, I don't know.
If you sort of twist this by square root of n times log or something.
But you're going to lose this linearity. So this whole picture works. So it's going to work if you take square root of any rational number times n, because there will still be linearity if to a congruent subgroup. But the moment you destroy this the method will stop here.
In fact, if you look at, say, square root of n times alpha, where alpha is irrational, doesn't that also look like?
Yes, correct. Yes, pretty much any reasonable sequence you come up with that's equidistributed will give you exponential distribution. Well, numerically.
Okay, any more questions? Okay, so let's say that.